I want to take this opportunity to do a quick review of a research program I've been conducting a little bit at previously at IBM and now at Google on one line of work that is around text input. It's a research review, so it's clearly biased towards the work published by these co-authors. Some are actually one of them, at least one of them is sitting here, Mitchell, and many other interns, colleagues, collaborators at Google and elsewhere. So I'm mostly presenting joint work with them. So therefore, it's not a comprehensive literature review. So I may not have opportunity to give credit to some other people who have done similar work, either prior or after our work. Also when Michael and James invited me back to this seminar series for the third time, I was hesitating a bit because being at Google, most of my time are spent on, along with colleagues, to work on products that get launched to billions of users. So there's a lot of excitement as well as a lot of attention needed to a lot of product details. At the same time, I also enjoy to do academic work. So juggling between both is quite a struggle. So I was hesitating whether I would be able to find the time. And then I told Michael that I will do it if I can cheat a little bit. That is, I will do the same work for the same assignment. I was submitted to two places. One is Stanford, the other will be a keynote at the upcoming IUI conference in Cyprus next week. So because of that, I want to tie this line of work from IUI angle. And indeed, IUI as a research community, it's a little bit of offshoot of Kai, was formed in the AI winter era, and now AI is in full swing again. So I expect the conference to be actually going to get a lot more interesting as well. So what is IUI? I look at the conference website. It basically says IUI is where HCI meets AI. That's a pretty descriptive definition. I also looked up on Wikipedia. It's a little more informative. The first paragraph of Wikipedia on IUI talks about Microsoft Clippy, which is not a very flattering way of defining the field. The second paragraph is actually quite insightful. It says basically IUI involves the computer side having sophisticated knowledge of the domain and or a model of the user. And to me, that actually is quite a good definition. That is, you have either domain or users' behavioral knowledge, or ideally both, and to use that to help with user interaction. So why bother? Why IUI? Well, one word, complexity. So as we can see or experience, you'll have very powerful computers that when I was doing my PhD, my advisor had to buy a SGI workstation that costed about $250,000 at the time to do my PhD work. Now, I actually, just 2 years ago, I sent him a phone that, if you look at the Wikipedia specification, it's greater than the $250,000 workstations I used on every single dimension. But along with that, it also comes with a great amount of functionalities and features. Even like product managers, UI designers, engineers, developers of the same product do not necessarily know the existence or operation of all the features. So there's a great deal of complexity when it comes to user interaction as well today. Something as like, for example, do you know how many settings there is on your phone and how many different ways to configure your phone? It's actually rather complex. And that level of complexity is actually increasingly harder to manage with a traditional direct manipulation, 100% direct manipulation approach. Something as mundane, as common as, say, just a volume control. Seemingly very simple, but when it comes to it, it's you're controlling the volume for the future, or what's happening now, or is it the media, is it a ringtone, is it alarm, and so on and so forth. And sometimes it can be quite critical. This is about 8 or 9 years ago. I literally ended up in the hospital because of just a volume control, because I was using an iPhone at the time. I had some dental work. My dentist prescribed some antibiotic just as a preventive measure. And he did warn me that if you have any problem, any symptom of antibiotic complication, call me. And sure enough, in the afternoon, I started to have diarrhea, and I was worried. So I called him. I said, but he wasn't in his office. I left a message. I asked him to call me back. And I tuned the volume all the way down, all the way up, so that I could hear it, and I continued to work. And I never received his call. And then I realized I had to go to the hospital, and it was that bad. It turns out the volume all the way volume up doesn't mean the volume is actually on at all. So anyhow, there's just a great deal of complexity to the truth that he did call me, except I didn't hear it. So I went to the pharmacy first, and eventually took the wrong medicine, eventually ended up in the emergency room. It was actually pretty bad. I stayed in the hospital for the first time in my life for 3 days. It wasn't a fun experience. So the point is that just human-computer interaction is already complex, and often can be, and it's only going to get more complex, and sometimes very intense. One of the most intensive interaction experience is actually text input. So text input is, in general, it's a difficult and acquired interaction experience. You may not realize that because you already spent years and years of learning and acquiring that skill. And it's a human endeavor in terms of coming up with technologies to enable efficient text input for centuries by now. And the background is a typewriter that everybody once in a while wanted to reform and change and reinvent. And here I want to just show a fun video of an invention.
The tech world is buzzing over Apple's latest must-have gadget, the Macbook Wheel, a revolutionary new laptop that does away with the keyboard. Tech Trends reporter Jeff Tate has more.
Thanks, Andrea. Say goodbye to the keyboard and hello to the future of laptop computers. With the Macbook Wheel, Apple has replaced the traditional keyboard with a sleek, touch-sensitive click wheel. Apple CEO Steve Jobs introduced the product yesterday at the annual Mac Expo. Senior product innovator Brian Gilman says the Macbook Wheel will make typing a thing of the past.
At Apple, our philosophy is create products that are simple to use, and nothing's more simple than a single giant button.
Gilman showed me how the revolutionary new computer works.
Just open the Intuitype alphabet menu here, scroll to the letter you need, see? And center click to select it. Then click again to capitalize, and repeat this process for each new letter. It couldn't be simpler. You can also let the predictive sentence technology complete the sentence for you.
Gilman says the MacBook Wheel has also simplified the organization of files, so searching your hard drive will be a snap.
Just press both sides of the wheel concurrently and center click, and there you have an alphabetical listing of every file on your hard drive. Everything is just a few hundred clicks away.
Apple is calling the MacBook Wheel the most intuitive product ever designed.
Here at Apple, we like to think that we're giving customers features they don't even realize they want yet.
While the MacBook Wheel won't hit the shelves for another 3 to 15 months, many Apple users already have it on their wish list.
I'll buy almost anything if it's shiny and made by Apple.
Alex Zalbin was one of the lucky few to get to try out a Mac Wheel and spent 45 minutes typing an email to his friend.
I never really realized how much I hated keyboards until I saw this thing. I like how the email automatically says sent from a MacBook Wheel. That way people know you have one.
With a price tag of just under $2,600 for the lowest lowest-end MacBook Wheel, it is an investment. But the super-thin laptop features numerous innovations like the new ultra-thin Hummingbird battery, which can power the MacBook Wheel for a full 19 minutes before needing to be recharged. And the computer...
How do I get back to it? Okay. It's just, it's fun, but it's not meant to be completely comical because there's actually very interesting points here about IUI, about how you can predict or should not predict, or how you should or should not predict, suggest information as a way of helping the user. The idea of like bringing down all the lists in the file system, as well as predicting every sentence you may use, and let the user to choose, is actually quite relevant to the current talk. So I'm running some mode. Okay, let me get back to it. Okay, that's better. So one of the basic ideas of IUI, of using machine intelligence to help the user, is to predict and suggest to the user. But suggestions actually has cost. So here is a study we published last year at CHI in San Jose, where we actually studied a common technique that is essentially used in all software keyboard today. Actually, prior to that, always used in Chinese text input for many decades before, as well as in the AAC accessibility community for people with who needed alternative way of communication. The idea is that as you give partial input, the system predict what you may need and give you multiple choices or one. Initially, the iOS design give you one choice, and then everybody pretty much in the past few years focused on 3 suggestions for various subtle reasons. The question is that if you make this suggestion, whether the user should or will take it, and why. There's actually cost associated with suggestion. That is, there's a utility of using that suggestion, but there's also a cost associated. The cost being at least 3 aspects of it. That is, you have to attend to the suggestion, you have to look at it, and you have to evaluate whether the suggestion is correct, or one of the correct ones is among the suggestions. And then, if it is the right one, you have to select it. So if I type TH and it suggests E, then I have to look at the E, look at it knowing the E is there, and select the E. Then what's the point? I may as well just type letter E. So all this cost combined may outweigh the benefit. And that's a simple way of looking at it. And it's pioneered by Stuttgart and others in terms of modeling elemental steps of interaction that will give you some sense about the interaction design efficiency or design goodness. But it turns out it's also a lot more complex than that. So this paper was actually done in maybe around year 2012-ish. We actually did a lot of modeling work for this paper. That was the primary purpose of this paper. But then Kai rejected it. Everybody has rejected papers, even James does. And then we resubmitted as a short note that's only giving the empirical results without the modeling part. But what we can see is that it's actually far more complex than designers think if you only think about the benefit of this suggestion. So you can present the suggestions. The system can always has best guess, always has best predictions. But it also should have an internal confidence estimate. So you can make the system extroverted in the sense that the system will always say something regardless it's confident or not. Or you can make it introverted. It will never say anything even though it knows you really want this word. Could save you a lot of time if you take this word. Or ambiverted, that is gated by some sort of a utility calculation internally. So we tried these experiments, constructed the experiment so that people can take different UIs, and we come to realize users don't always take them. You can see that the black bar is the amount of time or tabs that could have been saved or offered, but what people actually take was much less than that. So people don't take every suggestion, even if it's correct. So their savings are a lot less than the theoretical estimate. And also, when they take it, you can see when they do take it. So on this side, extroverted make more suggestions. People also take more. When people take more, their average speed is actually lower than the actually introverted. That's no suggestion. You just type every single letter.
So,
Michael, yes, please.
like an interpretation of this would sort of be flow-oriented. That like it sort of breaks my typing flow to accept the suggestion. And I'm wondering, toward that, like. Conceptually, it seems like you could do up to, what is that, a 17% improvement or something like that? I'm wondering, is this sort of averaged over every key press? Like, because some of the wins might depend on how early it can do the prediction.
Yes. So that's the utility. That is, if I type acknowledgement a long word, I type AC, and I take that suggestion, the utility is much higher. So that's the modeling part that we factored in. So we look at that type of calculation as well. Yes, but it's also far more complex than that. Is people do like it, and also people use it not necessarily for keystroke savings, but more for when I'm not sure about the spelling. I use suggestion all the time when I type Chinese because my pinyin is so lousy. I just have to look and try my chance. Or people try to use that to verify, oh, that indeed is a correct spelling, before they commit to it. So there's other choices. But still, this topic of suggestion, the cost of suggestion, or completion for that matter, is pretty deep, and it's a very central challenge to IOI. For example, we now have Google Home, we have Siri, we have all kinds of assistant. That's all based on some sort of prediction, based on a little bit of information you give it, and it just believe that it will give you. And sometimes Google will say, I don't know that yet. But these are all still ongoing research challenges. I don't think we get a very good hang of it.
Does that mean that your study in some ways is a pessimistic view of suggestions? Because if it's a study where I have to take a sentence and transcribe it, like spelling is going to be less of an issue because I can see it right there, whereas the case you just said, if I had to think of it, I might need that help. Yeah. So your study might under support how important that is.
Yeah, I actually, I'm sometimes, just look at the most aggressive use of this today. And it's also very clever use of today is in Google Gmail auto reply. So you don't need to give any input. It guesses you wanted this short sentence. James, that's great. So, well, sometimes that's what I want to say. And the evaluation cost is not that high. The attending or the motor selection cost is not very high either, but the potential gain is very high. So I don't have to type anything. But it's fairly introverted. That is, it doesn't say that all the time. It only say that when it believes that has high chance to hit you right. And you have your own judgment. People have their judgment where this is going. The design is quite conservative. It only predicts most common answers. Essentially,
Does it adapt? So if I use it a lot, does it figure, hey, I'm more of the person who kind of is willing to take that, so it should like show me those more often, or is it
I don't know for sure. I suspect not.
Okay.
And I'll touch on personalization a little bit later. Let me go back. So, but suggestion is not the only way to use machine intelligence. The other way to use machine intelligence is to correct, because humans are generally not meant to be very precise, very mechanical at doing things. So you can use the same kind of machine intelligence to correct or complete users' incomplete or partial or erroneous or sloppy input. That would be another way to help the user. And there's always a speed accuracy trade-off. If you allow the user to be more sloppy, and then it can be also faster. So how do we do that? In the context of modern keyboard, this is what I call the standard model, and it's quite straightforward. So basically, by definition, what we want is that user has some sort of input, and this input is expressed as a signal. That signal can be a set of touch points, or a sloppy gesture, or a combination of voice of something that can be anything that is a signal. And the signal has to be understood by the system. And the system look at the signal, given the signal, will look for all, in theory, all possible words. Of course, in practice, it has to do clever pruning and traversing to find the right word quickly to give you the word it thinks you want. And that's the basic problem by definition. So this is what it does. But how to do that, of course, there's not a simple lookup table. You can look for every signal and give every word. What you need is where the AUI comes in. That is, first of all, you need a knowledge about the user or the new user behavior specifically. That is, for any given word, how likely the user is expressing it with the particular signal you receive, the signal S. That's every given word. What's the probability of user do it that way rather than some other way, and what's the probability of that? So that's what we call a spatial or motor model, or user model in general, user behavior model. And then with this knowledge, it's almost a complete reverse of the decoding of the problem itself. It's a given signal, you want to find a word. Now you have a model of given word, you know based on your knowledge of the user, you can infer what's that word at what probability. And then, thanks to the famous Bayes rule, you can flip side and multiply that with the prior probability of that word, which is inferred from context, and that is commonly known as the language model. Or you can also say that's the domain knowledge that's embedded in IOI for text input. So that's the general framework. Every system, I'd argue, works this way one way or another. Maybe they're not aware of it, maybe it's indirect, but it's one way or another, this is how a modern keyboard works. Now, the question is that where do we get this knowledge or user models, and what are they? So, James, you had a question. I really welcome questions because this talk is a lot of different things, and giving me questions will give me a clue about how to steer it. But on the other hand, I do want to get to the end of it. Let's say, so what's the user model of when it comes to touchscreen interaction? The first thing comes to our mind is the famous F word in HCI, namely Fitts law. So, but interestingly, this is a foundation piece to GUI interaction design. It actually doesn't apply to touchscreen. At least doesn't apply to touchscreen strictly. So Paul Fitts himself did experiments with stylus, disk transfer, packing whole, kind of three types of tasks. In the 1950s, Stuckart brought this to the HCI field, or even before HCI field was formally formed in 1978, to study the mouse cursor behavior, as well as joysticks and other cursor control behaviors. But basically, it's based on a single point. So the absolute control precision isn't a problem. The problem is the relative precision. That is, how relative the target is tolerant to errors in comparison to the amount of movement you have to make. So we have to do a remodeling of Fitts law to provide a fix for finger touch. This is exactly what we did a few years ago, called the finger Fitts law. So basically, from the traditional Fitts law, we have to subtract certain amount of absolute amount of error due to the finger imprecision, commonly known as the fat finger. So this is really a formal solution to the fat finger problem. But still it has a problem when it comes to keyboard, because it only applies, Fitts law only applies to one movement, one point of movement or one point of travel. But in reality, some people type with one finger, but a lot of other people do two thumb or one thumb, and still others would do all combination of three depending on the situation. So that makes it very difficult to apply a simple Fitts law or even finger Fitts law to model it. So what it comes down to essentially, it's not a complete model, is that we know the distribution of the model for the touch points. If you look at the touch points, basically it's a Gaussian distribution. Look at them all together, collectively, on this side. Use one finger, the spread is, the Gaussian distribution spread inside and outside of target key. It's a little less than thumb. Thumb would spread even wider with two thumbs, slightly wider. But you can view everything as a Gaussian. And once we have that Gaussian distribution as a user behavior model, then factor that into the general equation I listed earlier. You can solve this quite easily into a very simple operation. Essentially, the decoder does is that measuring the touch point distance in case of touch to the center of each key, and that combined with a language model by simply a log normal combination addition, you will get the probability cost of every single word in the database, in the language model. So, and that can be solved easily, very elegantly, and comes to a very simple computational operation as well.
A quick question on
yes.
Are people at all optimal in this, in the sense that, like, do we tend to pick fingers that do a good job, or are we actually blind to what actually works? Or is the actual effect of it so minimal that most people wouldn't notice the difference, and so they don't adjust their grip to type effectively? Like, how much of joint learning is happening here?
Yeah, that's a great question. I don't have an answer for it. The example is that I feel sometimes people will find the best way for the situation. Like when you're walking and you're also talking or holding coffee, you use one thumb. Yeah. You have the time, you focus, you use two thumbs, and sometimes you use one finger. It changes. But on the other hand, I did not know a good way of doing typing is actually holding with one, for gesture typing, is holding with one, more or less with one hand, but the other hand is doing with a thumb. That's turned to be a more stable control loop than this. Your friend Tom Ouyang told me about it, and I really like, yeah, after a while, I did find that it's most preferable. But prior to that, I didn't know that was, as a end user, I didn't know that was actually preferable. So I don't have a complete answer on that. Yes.
But nowadays, aren't a lot of us sliding rather than pressing keys?
Yeah.
So how does it make?
We'll get to it. Yeah, we'll get to it. Yes. Now, but what's interesting is that these different what we call hand postures will give you very different distributions. So on this side, you can see if you use a single finger, you tend to type lower than the key center by a larger amount than if you type with a thumb and so on and so forth. And laterally, you can also see some keys tend to be typed more biased towards the center, and others are more biased outwards. I think there's this word typed outwards. So it really depends on both the hand posture, which key or which location of the key, because ergonomically, obviously they're different. When you try to bend your finger or trying to extend your finger, those will all cause different biases. So if we know these biases, then we can factor a more precise prediction about how you would express each letter, and therefore you can have a better model, better spatial model or user model. And then you'll give better prediction, therefore better correction as well. So that's precisely what we try to do. That is, we build models for each finger posture as well as individual, as well as you imagine it's personalized, it's to the user, to the key position, to hand posture. All three factors, then you will do the best possible job in terms of decoding for the user. But however, that means you have to know they are in that mode. How do you know? If you have a very sophisticated sensor, maybe you can look at the user and user's hand and know, but that's quite difficult to do practically. So we have to infer from behavioral data backwards to know, to do a classification such as a SVM to find out whether they're doing typing with one finger or typing with two thumbs, or one thumb even. So
another question maybe a similar one to this. Okay, so I'm seeing a character error rate going down by about a full %, which could translate into tens or hundreds of fewer errors a day.
Yeah.
And I'm wondering if we blinded people to which condition, which model they were in, do you think that they could actually figure out which one was better or not? Like, is this a difference that people can perceive? Is it something that maybe they would get a sort of a sense intuitively that maybe it's just a little smoother, but they would never pinpoint it on the model? Like, I'm curious how much of this actually percolates up, into the perceptual layer or the cognitive layer, and how much of it is left below.
But again, that's another good question. I don't think we have a good answer on that. On one hand, again, you feel just let's say a percentage of change. 1% WER reduction in speech recognition would be a huge breakthrough that people don't believe. You can achieve that much. So usually they talk about relative WER. So then if you begin with 10%, you reduce 1%, it's 10% of what's remaining. That's how they generally report it to make it sound a bit more. But also maybe that's what matters. But what's interesting is that, so to the end user experience, is that 1%, how much that translates to their overall user experience? It really depends. It's hard to say.
I wonder
if
there's a halo.
And whether it's perceptible or not.
I'm almost imagining a 2x2 study wherein like you're manipulating the model, but also manipulating, say, like a mediocre to a good interface. And I wonder if people would attribute the difference, say, to a better interface, when in fact what you're doing is changing the model. Like it's sort of like it's just smoother. I don't know how, but it just feels better somehow.
Those are great research questions. I'll touch it on again later.
Intern with you, clearly.
Yeah, wow. or we can have joint interns to do just that. But the next story here, those character level reductions, those are at character level as you type each character before a full decoding is applied to. When you apply a full decoding on it, that leverages a lot more power from the language model. These are pretty much washed out. So at this level, but again, this level is also assuming detection ability and so on and so forth. So it's an interesting idea. So the key idea here is the back off. That is, when the system doesn't know what specific hand posture the user is doing, or which individual that was, you apply a general base model. As the system gains confidence to infer the mode or state or particular state in this state transition paragraph, a graph, and it will apply a more specific model. The last thing you want is that it applies the finger model to the thumb and then gets you even worse results. That's you don't want. So, but nonetheless, all things considered, this is still very, very, at this moment, not worthwhile to do. So we're still basically applying a general model, a base model. So the other way to use IUI is to just reduce the amount of work user has to do. So earlier we talked about ambiguity in touch, but actually gesture or sliding keyboard from one letter to another, by definition, will give you a lot more ambiguity. Often there are many, many letters along the way that's not what you needed for that word. So I've talked about this before, actually, in the last PCD I gave about 7 years ago from a different angle. That is how we consider this a learning problem, and how do we facilitate learning, and how do you facilitate the transition from an initially video-guided behavior to a more recall-based behavior. I'll just do a short video to refresh that a little.
Shark is a pen-based text input system. It combines a stylus keyboard with pen gesture recognition technology. The keyboard layout can be either the standard QWERTY or the atomic layout shown here that is optimized for stylus motion. For each word in a large lexicon, a shorthand symbol or a sock graph is defined by connecting the word's letters on the keyboard. For example, the word word is represented by the letter trace W-O-R-D. A novice user can look at the keyboard and trace the letters of an intended word. Here the user is writing the phrase, "The quick brown fox jumps over the lazy dog." Unlike speech recognition, error correction is relatively easy with the pen-based shark method. If a mistake is made, the user can select a correct choice from the unbest list embedded in the text stream editor, or delete an unwanted word from it. A new user can also use the animation feedback feature to learn sock graphs. The animation morphs the user's pen gesture to the ideal sock graph of the word the system recognizes. Over time, the user may remember the shapes of those well-practiced words and shift from visual tracing to recall-based pattern gesturing. As a result, the input speed may increase dramatically. We use a multi-channel pattern classification system to recognize the gestures drawn on the keyboard. In particular, the shape channel looks at it.
So this was really by internet or mobile age. It's really ancient history now. It's 2000, started in 1999. The video I was showing is 2004. That was made during our submission to WIS 2004. That we were given what was called Lasting Impact Award just a couple of years ago. But at the time, the press really loved it. They even called it new way of writing, Mercury News, and widely syndicated by to some 100 newspapers around the world. But most people were quite skeptical that whether there's something in here that's actually really worth a business attention. So today, it is in both iOS and Android platforms, and it's freely available under many brands made by many engineers and different companies. I won't show the video, but I want to talk about, so how do we evaluate the text input systems? This has come up a few times at lunch as well as during this talk so far. Text input evaluation is really difficult because there are so many aspects of it. For example, there's always a speed accuracy trade-off. So if you do it, make a lot of mistakes, and you can type very fast, and that doesn't mean it's necessarily better than a slower one, but with no error. But yet, when you get results that changes in both dimensions, there's no model that tells us how many errors worth how many words. Traditional typing contest, every keystroke error would count as 5 words or something like that. So, but that's a kind of arbitrary. So how do we deal with that? The research field generally don't seem to want to recognize evaluation is just very complex. Evaluation always answers some questions and raises many more others. But that's just like this is by now about 20 years ago. James probably know that provocative essay I wrote in response to Henry Lieberman. He argued about evaluation is the enemy of research, and I said evaluation is the only way of doing research except all others, paraphrasing Churchill in terms of democracy. But now we also know democracy doesn't always work either. But still, it still is the best. So in text input, how do we do this evaluation? There's also difficulty in terms of human learning. So any given method, it takes a lot of amount of time to master. So this leads to difficulties in terms of like traditionally the debate between Dvorak and QWERTY keyboard. To date, it was not a resolved a question, a topic. Also, once the keyboard is smart, in the sense that it has a language model, then there will be issue of a language coverage. For example, if you have a smart keyboard, all what it does is one word, like W-O-R-D, and whatever you do, it will give you the word word. Then for that word, definitely you can do much faster than any other input method. But it doesn't have any coverage. So if you want to have coverage, our traditional way of studying text input, like having a few people typing on a method for an hour or two, or even for a week, isn't just going to be enough to cover the language phenomena. We can also use logging to measure results, but logging has its own problem. Other than privacy, logging also doesn't give you the user's intention, so you don't know whether they actually made a mistake or not, and you have to guess that. And also, there's a real world versus lab context. So here is an example. We took this method by my former student Parola, who at the time was at the St. Andrews University, now he's at Cambridge, and his student Shyam at St. Andrews. We did a study that inspired by a common research method in the UbiCom field, that is, you embed the test in everyday life. You can call it experience sampling. Here is more performance sampling. So we prompt the user randomly throughout the day, 10 times a day. Either they are walking or eating or something, and ask them to do a short sentence. And the results actually are very different from lab studies. That's one thing. But still, the study results is quite complex. Here we can see generally there's some advantage to gesture typing or slide or swipe or word gestures than tap, tap, tap kind of a style of typing, generally speaking, but it's not completely unequivocal. The most unequivocal and comprehensive answer in here is kind of voting by hand in the sense that, so we allow the user to actually also use the method outside of the study. So we also ask them how often, before and after, how often do they use gesture typing versus tap typing. And you can see for participant 5 and 6 and 7 and 8 and 10 and 11, they had no use of gesture typing before. SGK stands for Smart Gesture Keyboard. No use of it, and they were either not aware of it or didn't use it. But this study itself, in the process, they got to learn this skill, and everybody become much more used than before, and some become 100% convert, like 9 or 3. Afterwards, they used 100% of the time gesture typing. And people started with gesture typing before the study and still ended up gesture typing after study. That is those two. So that's a clear, more comprehensive evidence that people do like overall better. But how do we parse that to individual aspects of the performance is still rather complex. So back to the theme of IUI, that is how much you want to help the user and how much you take that work to the system to do. Has many ramifications. One of them is that the gestures defined on QWERTY is actually pretty poor. It's all zigzag, very similar. Can we turn it around? Indeed, you can see from the video, the keyboard used was called Atomic. The idea was that the keyboard was optimized to minimize movement. As a side effect, it actually is also pretty good for gesture typing. This is the word writing on the keyboard of Atomic. And then more recently, we asked ourselves, this was with another intern at Google, can we actually optimize for clarity? That is, statistically, the gestures defined on keyboard would have less chance to collide with each other. So for example, on QWERTY, the word OR and the word OUR completely collide. And this is just an example. The remaining words actually are very, very similar. But if we allow to move the words around, letters around, then the shapes defined by this keyboard would begin to change. And then you can statistically using optimization techniques to push all words statistically apart rather than push them together. And that's what we call clarity. But clarity is not that easy to do, but still much easier to do than you think about. That's not the only thing that matters. Another dimension that matters is the speed. That is, if you push all the letters tend to be on the outside, the gestures will be more far apart, but every word you do a very large gesture. So we have to consider speed as well. And most importantly, we have to consider how easy it is to learn that key layout. So in here, we factored in the keyboard's similarity to QWERTY as another dimension. So if you look at just two of them, a little easier to look to see. This is gesture typing accuracy, clarity on this dimension, and typing speed on another dimension. You can see this theoretical prediction that QWERTY is right in the middle, and you can achieve better on each dimension and both dimensions. So the best is somewhere here that is better than QWERTY by a large margin in both dimensions. But still, it's still ongoing research because when it comes to learning, people have a great amount of bias in terms of investing time for the future versus my time today is the most valuable by a huge margin. So still ongoing work. Now let me switch to the domain knowledge in text input. That is language modeling. So language modeling traditionally is quite simple. It's just you can view it as a list of words with set probabilities, known as n-gram probability, like thank followed by you is thank him is well, less likely, but so you have you have a list of words that follows preceding words, known as n-gram models. More recently, there's more neural net-based representation of language models, which can be more compact or more efficient, or more information. But the concept is quite simple. The actual production of language model is very, very complex because it really has to do with outcome, has to do with the quality of the training corpora you supply to the trainer. There's also filtering problems. That is, if you just get a huge amount of text from the web, you'll find all kinds of inappropriate, insensitive, or simply plain wrong language models. So you have to do proper filtering, and then there's policy issues. Like user will get mad at you if it gives you a profanity word by mistake, but user will be, some other user will be very, very outraged that what, your keyboard doesn't mean to use the F word? Come on. Also the development requires training, dev, test set to be separate, and so on and so forth. So anyhow, a particularly interesting topic for the text input area, which I mentioned briefly earlier, is personalization. So if we assume people talk somewhat differently, then you want to adapt to that particular user's style, and how much gain that would give you. So this is a paper we published a few years ago that measures when you don't use language model, the keyboard becomes dumb keyboard, and you'll make about 40% of errors. In fact, quite large. But as long as you apply a background model, you can reduce that to, this is a simulation study, to around 6%. And then if you apply a personalized language model, you get another 1% absolute reduction, or 20%, about 20% relative reduction.
Presumably this would depend on the typing task, because if you're trying to personalize, like I may actually be typing different things than whatever some generic task set would be.
Yeah, and it's definitely very much ongoing research. But it also implies, how do you study that? How do you study a language model that adapts to the user and actually has a long-term benefit? So how much you can afford a long-term observation. So this is actually quite creative in this study, is that we took the gold mine of NLP that doesn't have a privacy barrier, that is, namely the unrun email corpus. And that has many years of history, all tracked to individuals. So you can know if I have this model for this person, for Geza, for example, and 4 years later, how that algorithm will do to his typing. And actually typing, so we'll have a user model emulates Geza to type in particular way, particular style, in particular bias with error. And then you can simulate this process with a new language model versus a A/B comparison, and you'll find out what this is how we got the results. But then you also observe these things, like you adapt, there may be improvement, but all of a sudden, Unrun got sued. Everybody's talking about different things, and then the model would may not behave as well as used to, and then it needs readaptation and so on and so forth. So it's very much ongoing research that is still not conclusive, but generally there's some gain to be made in personalization. Okay, so I think I'll skip this one. I'll talk last topic that Mitchell did at Google. That also concerns the theme of this particular talk, that is how much IOI can help user interaction. So text input on phone was difficult enough. On a watch, a smaller steel computer, the fat finger gets really fat relative to the thumb. To the watch, it's about 1/3 or 1/2 of the watch. So how do you do that? How do you do a keyboard on a watch? The traditional HCI method, some very clever from our own field, but I would say more conventional field idea is that, well, since the finger is too fat, what do? You make the keyboard virtually more error tolerant by breaking down each key to 2 steps. Like you tap once, the keyboard zooms up, and you tap second time. This time your finger is not as fat as last time, therefore you get it, right? Or you shift the keyboard, you only display half the keyboard at one time, and so on and so forth. You can think of many, many methods to do this. But the general idea is that you break down the task into more steps and more elements. It's a reasonable idea, but it means the user has to do more work rather than less. So we first thought about this, even myself thought, yeah, it's kind of crazy. But let's say human would take some hit by trying to be a little more precise, but let the ambiguity or the errors to be handled by intelligence, by the machine. Maybe the machine can resolve it. So sure enough, this is what Mitchell did. Not only, actually this is real, so we can show the video.
We present WatchWriter, a finger-operated keyboard that supports both touch and gesture typing with statistical decoding on a smartwatch. Just like on modern smartphones, users type 1 letter per tap or 1 word per gesture stroke on WatchWriter, but in a much smaller spatial scale. WatchWriter demonstrates the combination of human motor control adaptability with modern statistical decoding and error correction technologies developed for smartphones can enable a surprisingly effective typing experience despite the small watch size.
So you can see the results on the lower right corner. The either tap or gesture on watch by using statistical decoding went by a fairly large margin. It's usually not that obvious, but in this case it's very obvious than conventional, purely manual approach.
So a total novice question here. What's the typical WPM of like typing on a smartphone?
Today, I would say around between, on average, 30 to 40 words per minute as the average. The study tend to vary quite a bit, but that's my best guess based on all kinds of evidence. For example, one of the slides earlier, let me have that. So this is the study on the top, WPM, yeah, 38, 30 some. This is, again, one study. That's another difficult question. That is, what's the typing speed on keyboard, on regular QWERTY keyboard? Traditionally, secretaries can only be qualified as a secretary if they type 60 words per minute. but my sense is that that varies widely. Most people type much faster today. Yes?
Yeah, a question on that variation. So in terms of what are aspects of people that cause that variation, I could guess like a list, say like working memory capacity, maybe conscientiousness or motivation if they're trying really hard. You mentioned motor control for the smartwatch. I would imagine like proprioception, like knowing the space between fingers. What else is determining the learning curve between people?
I don't know, and I think like this is actually how I started this line of work. At first, I got into virtual keyboard studies when I was my friend Scott McKenzie was doing some studies presenting at the CHI, and they were doing keyboard optimization. Say, well, you arrange keys, and you can. At the time, it was stylus typing. You tap with one stylus. It turns out actually other people in the AAC field have done this much earlier and much more aggressively for a while. But I was sitting and listening to the talk. I said, well, so it's only 26 letters. So what people are learning? Why it's so difficult to learn? Can we make the keys somewhat different? Can we make some keys stand out? Can we add more visual features? Would that make the learn faster, and so on and so forth? I did this research, not covered today. We published a number of papers. I had one intern from Stanford Psych Department, Paul Lee, and worked on this quite a while. Frankly, the more we study this, the more we come to conclusions. We just have no clue. We just have no clue how people learn. We just don't. One factor, time on target. The more time you spend on it, the more you learn. Other than that, I actually talked with a Santa Cruz psychologist, a very famous one, and he said, oh yeah, we know that. He does a skill acquisition kind of study. He said, we all know that. If you get a doctor from 200 years ago to ask a doctor to treat your today's problem, the doctor has no clue what to do today. If you get a teacher from 200 years ago, a good teacher, today that teacher will be still a good teacher. That just means so much about learning is a practice, not a theory. That's kind of interesting. Anyhow, so yeah, that's still a great deal of interest to me and many other researchers. So to welcome more work in that area in terms of learning. Actually, literally, that's the next breakthrough, I think. The paradigm of gesture typing can truly get to the notion of shape writing. For a while, called shape writing, that is, you really remember the shapes. But that means we'll have to change the keyboard layout. That means we'll have to find a way for people to learn. I've learned one layout like Atomic, and I have other users still going after me today saying, well, why don't you bring Atomic back? But I just felt it's just too hard to learn. How we can find a good learning method. Maybe just like a simple game, I don't know. Let's see, let me close by saying that the rapid breakthroughs in machine learning is also bringing more and more opportunity to HCI, but also brings a lot of challenges. As we get better, the user perception or experience often gets either worse or the user expectation raises. So there's all forms of uncanny valleys in HCI that I think we as a field should invest more and do more research on. And the other challenge is that most successes in machine learning comes from unnatural phenomena, like large amount of images, large amount of speech data that can be labeled, usually in case speech, actually done by human transcription. Or even machine translation also has already existing translated text as labeled data, large data set to help the machine learning algorithms to find the best representation. But in HCI, behavior-wise, user behavior is interactive. It's not, this is what you do, therefore that's the right thing, that's the wrong thing, or every gesture is a word. These are, that gesture is somewhat defined by your design. So it's also user will change it. Like in gesture typing, people start with going from one letter to another. But over time, they will become more fluent and they will cut corners. Also, knowing the system can take that tolerance, they become more and more what we call minimum jerk minimization, a model I skipped today. My former intern, now his colleague, will probably have a chance to talk about that. But the difficulty is that there's not an easy way to label data. Therefore, there's not an easy way to train a neural network to do interaction algorithms easily. Evaluation continues to be a challenge. So I'll stop there. I'll already overrun a little bit. But thank you very much for your attention and ask more questions. It was really good, very good. Thank you.
So in your original video for Sharp, you had this feature in which like it showed after you put like this is the optimal one. Did that like ever show any benefits? Because I know it's simply not
good point. So that's related to the early question of teaching. So the idea is that you draw a gesture, and the gesture animates to the ideal. It tells you the amount of tolerance it has, and also tells you what the ideal gesture is. Or when kids make a mistake, it animates to a different word, and you understand, oh, that's the word I really was more closer to than the word intended. And it's a fun feature, but generally wasn't magical. The reason is that users' attention is always ahead of the task. So when they type one word, gesturing one word, their attention is on the next word or next starting point. So they don't usually pay attention to that. So there's that challenge. Yeah.
What do you mean by uncanny values in this context?
In this context, actually, keyboard is a little harder to say, but other predictive methods, like let's say we want to predict, instead of you go look for 1 in 1,000 apps you may use for this moment, why doesn't the app just launch itself? Or at least presents itself, say, well, here's the app you want. And we have this both on the iPhone and iOS today, iOS and Android today. But that prediction can be like simple as something just recency. What are the recent used apps and which displayed in one place? And you look for it. And that cost, user expectation cost, is much lower than, say, it also consider location, time of day, or some other magic signals and use large amount of signals and present somewhat better, but less reasonable in the sense that you can expect, it's hard to expect what's going to be presented. And that, in a way, you have greater cost as you get closer to perfection than not. That's one form of uncanny valley. There are many other forms I find. I just think it come up quite often. Not necessarily in the original sense of like when you have something, a robot that looks like a human, it's actually more uncanny, but in a broader sense. And we certainly see these in products like assistance kind of type of products. That is, if it's just I do search and I know what I was looking for, it gave me results, and I know that's not the right one, but I totally understand it. I sort of am more forgiving, but in a conversational interface, it gives me back something that's not appropriate or ridiculous, and the user gets less forgiving. Yes.
So with more opportunity for more spatial gestures in mediums like VR, have you thought about how you can transfer your work here to completely new spaces for areas where text input isn't really innovated upon?
There are actually papers on that already. A particular form is that you make the shape writing gestures in air with some sort of finger tracker. That's people have done that. Usually not very good. Surprisingly, the surface has a lot of very good interaction properties in the sense that the moment you touch the surface, your finger knows you touched the surface. The surface knows you touched it. So there's no ambiguity in terms of segmentation. If you do gestures in air, where's the beginning, where's the end? If you use a clutch, it gets awkward and all that. But again, maybe we'll have better intelligence will have better user model, better domain knowledge, will be able to handle more ambiguity. That's still very much open question. Yeah.
Hey, David. You know, I have a long history with these systems. One of the things that I find most frustrating is when I'm trying to type a word and it can, like more than once, it will suggest the wrong word or convert it into the wrong word. And I wonder if there's been studies done as using as a variable the amount to which a user correction or a choice of the algorithm's first choice, the amount to which that changes the program behavior and whether that has, significant effects on long-term learning.
Yeah, two answers. One is that yes, actually one of the basic logging-based metric is the amount of time, the percentage of time you take the suggestion. So when the word is come out of the algorithm, especially when it comes out in case of tapping, it's different from the literal string you tapped and give you an alternative. The percentage was taken by the user without overriding it is the basic indication of how well we're doing with our algorithm. So that's the one answer, the more general answer. But the flip side, the other answer is that often these are just viewed as bugs. They are indeed bugs. Bugs in the sense that you actually had a word that should have been in your language model, at least a personalized language model, but it isn't. So that's just, we view it as a bug, which it just shouldn't happen. So either our production system didn't consider a particular use case, like your contact or a friend's name in Facebook should have been in there. We didn't have the pipeline to actually feed it into it, so therefore didn't know that name. And you thought, we have this kind of internal feedback, and people got outraged. How come my son's name is not in the dictionary? It's just ridiculous. Yeah, so that happens. Yeah, that's just a bug in a way, but it does again reflects the coverage and domain matching of a language model with the actual use.
All right, now with that reminder that we should never take our phone typing for granted, let's thank our speaker one last time.
Thank you.